Swayam Prabha. Digital India. Educated India.
Let us now look into how the control plane operates to build the forwarding tables. Consider the topology shown here, and on top of this, now if the control plane has to interact and build the routing information, we need to make these routers that are spread across in the network to interact and build the information. And this is done by facilitating each of the routers with a specific routing algorithm that would run in them. And this could be either the link state routing algorithms that are based on the entire flooding infrastructure, or it could be the distance vector that would just exchange informations with the neighbor. Eventually, when they converge, each of these routers will have the information of the network topology, and then they can run the specific routing algorithm and basically reduce and deduce what would be the forwarding tables in order to reach from one point to the other. And this way, the routing algorithms in each of the routers would set up their own local forwarding tables. So note, the interaction happens at the control plane for deducing the network topology information, and the routing algorithm would be run on each of the routers to provide the local forwarding table. Now, let us try to fit the two of the abstractions that we just discussed into this model and how we would have that paradigm shift. Here, if we take the same base model, what we observed is that the control plane is all embedded within each of these devices. And hence the routing algorithms are all run locally on each of the devices. And our first abstraction in this case was to provide a global network view. That means we didn't want each of the router to have the network view that is global but local to itself, but a view that is common across all of these routers. And to do this, what we would have to build is ensure that we have the information that is extracted besides these indistinct individual routers. And that way, if we shift the control plane up, that is, externalize the control to a remote controller, which is now able to map and spawn the requirements to build the global view, then we would have achieved our first abstraction. And what that means is to take out the routing algorithm that is running within each of these routers and externalize it to a separate server machine that is running outside. And this remote, what we call as a remote controller, is our implementation of a network operating system. And then to speak of our means, once you have a remote controller that is able to get the global network view, it can compute the global routing table. Note that this routing table reflects to the global map independent of each of these routers. At this point now, if we have to plumb the forwarding table information back, we need a mechanism to put the information that is derived at the remote controller to be updated at each of the routers. And for that, we use these control agents, or the controller agents, to which the remote controller can communicate and ensure that it can push the corresponding forwarding table. So this way, now we can fit, when we want to build this communication, we want to build a generalized forwarding model. That is exactly our abstraction 2. So that whether one of the routers is a Huawei router, one of the other is a Cisco router or an Arista router, it doesn't matter. What matters is we have a unified API to push the forwarding table into each of the routers. And that's exactly our abstraction 2, facilitated through a control agent that would run on each of these routers and ensure that this control agent will operate on a unified API model from a remote controller and then would do target specific aspects to eventually build the routing forwarding table into the each of the routers. And thus, we would have achieved our goal of decoupling the aspects of control and data to ensure that we are able to control the entire network homogeneously. So to sum up the software-defined networks in a nutshell, what it would look is the first is the separation of the control and data plane, where the control plane is basically externalized, and through this externalization of the control plane from the devices like these routers and switches, we have a chance to build a unified interface for operations. And what this also allows is a means to have a unified interface for also to configure each of these networking elements. And this is achieved through the generalized flow-based forwarding. And that's, for example, OpenFlow API, which would allow us to set the match action tables into each of these routers. And from the remote controller point of view, we have, having externalized the control plane, all the control plane functions can now be run on one single server. You don't have to worry about the hardware aspects of these individual routers, from which OEM the routers are coming from. All of these can now get abstracted and built on top of the remote controller in a common fashion. And this is our third aspect of control plane functions now becoming external to the data plane switches. That means they can be run on the commodity hardware now. And more importantly, now, because we have the control functions that can be run on our regular machines, the control applications become programmable in the sense that every individual can now program and control the way the routers would want to behave and dictate much more easily what objectives need to be achieved. So, through this simple decoupling of the control and data plane and centralization of the remote control, we are able to now see a paradigm shift in terms of how the networks can be operated and networks can be managed, and in a much more simpler and centralized way. And that's where the SDN started to gain traction and became very popular. And to fit it now in very simple terms, the centralized remote controller, the abstractions that it provides can be thought of as a network OS, and it would build the global network map and allow the control applications to flourish on top of this network OS, which provides the common abstractions. At the bottom, we have the barebone switches, where a control agent would be able to run and establish the forwarding model of providing the simple match action patterns to be run on these data plane elements. So in essence, the network elements like the routers and switches now truly begin to behave as data plane elements while the control is taken out. Nonetheless, it doesn't make these devices any dumb, unless how the misconception also has been that the SDN makes these devices dumb is not true. In a way, it simplifies these devices and ensures that now you can build the means to program any of these devices with a lot more ease and reuse the same code that you would build on top of the network OS for variety of hardware manufacturers or hardware vendors. And that's basically the openness and innovation that SDN tries to bring forward. So we may wonder why we should have a logically centralized control plane or a network OS. So we said, with a logically centralized control plane or a common network OS, the applications can flourish very easily because you have a fixed APIs to worry about. And that means the programmability is very easily applicable over these network OS than on the dedicated hardware software combinations that OEMs used to ship. So this would give full control and visibility over the entire network. Second, it becomes a lot more easier to manage the network because we are now trying to manage and configure the rules from just a single point. Not that we are avoiding the configurations on multiple routers, because we still have to configure the rules on each of the routers, but the decisions are taken centrally rather than the decisions earlier that used to be taken by each of the routers independently, which made it very difficult to debug and know which router has chosen what paths and for what purpose. But now we have a complete control, and that makes the configurations a lot more easier, and we could avoid any of the router misconfigurations that otherwise would happen, and we can even get rid of the count to infinity problems that you would have otherwise seen in earlier models. And this also provides greater flexibility. Why? Because now the forwarding tables, which can be built on each of the routers independently, we can base this not just on the destination IP, or rather the destination based forwarding, but make use of the generalized forwarding, where we can take into account the characteristics of even the source IP. So based on the source and destination IP combinations, based on the port or the protocol combinations, we can choose to have different paths that can be used for the same set of flows originating from the same source and ending at the same destination. So this gives a lot of greater flexibility for us to manage the traffic flows. And most importantly, now when we look at the second abstraction that we said, the table-based generalized forwarding, in a sense, this is exactly the programming of the routers in terms of what the data plane entity of the router is supposed to do. So the flexibility of how we want to program is offered at a single point at a controller, and that is centralized programming. So it becomes a lot more easier to compute these match action tables and distribute these tables across all the routers that are participating in the network. Unlike the earlier distributed programming, where it was a lot more difficult and you had no clue about what each router has eventually ended up. And there was no control either on how to choose the path, because that was all embedded within the routing devices themselves. And overall, such a framework leads to openness, that is, no proprietary aspects could hinder us from implementing anything new, as we have the same open interfaces on which we can build the networking control applications, as well as experiment on how to route and forward the packets at the data plane. So this automatically fosters for openness and innovation. And that's where SDN paved the mark and has been revolutionizing the networks, the way we deploy and the way we think of it. So to take out some of the specific insights here, with SDN, it all began with the centralizing of the control plane. And it's a very powerful abstraction, because now anyone who would want to communicate needs to just express the intent of how they would want to communicate, and rest of the complexities of making sure that forwarding tables, everything can be done, would be done through a programmable way at a centralized controller. And this centralized controller also means that it's a single API for the entire network. Rather than thinking of API for each box, where you would go to the routers and configure the parameters, which would differ from different hardware vendors. Now, no more of that hassle, and you can control all of these devices sitting at just one point. Now, the question may arise, like, when we have such a framework, wouldn't the centralized controller or the network operating system, the machine on which the NOS is running, be a bottleneck, and how would it really scale? And that's where we bring the notion of a logically centralized, but meaning you have one view of a system, but it doesn't necessarily mean that it is just one machine on which the network operating system is running. So we can in fact leverage the distributed systems techniques, that is, to build a distributed framework where the network operating system is a distributed OS running and replicated on several of the servers, which can basically coordinate and interact to facilitate the updates on to the hardware plane. Thus, we can have a centralized control. No matter on which of the device you would work, you would have the unified view, and we would also get rid of a single point failure. That is, even if one machine fails, one of the controller device fails, you would have other controller to work, operate on, and continue the operations. And as well, we could load balance across these multiple controllers as we scale the underlying network. Thus, these networks can now be provisioned by software, and you don't have to spend human resources in trying to provision and spend hours of time in getting the network set up. Going forward, from decoupling of the control and hardware, software control and data plane, the SDN have evolved a lot more towards bringing what we call as a disaggregation, and this disaggregation between the hardware and software of the networks, how we manage and control. And on the other end, at the application space, they have made the network operators' life a lot more simple by enabling the operators to just specify the intent rather than worrying about the nitty-gritties of how to make a specific policy be updated, or worry about the mechanisms that make the policy to be implemented. And this provides, in a way, the better control and better security to the network operators. So if we look into the evolution of SDN, we started and learned the journey up till here to say that we separate the control and data planes, and we would centralize the control into one, that's logical centralized network operating system. And once we do that, we also need the standard protocols to operate between these planes, that's control plane and data plane. So we'll look into next about the open flow. And with the evolution, what we see of SDN is not just the decoupling anymore. Like I said, this is to do a lot more with disaggregation, or in fact, you virtualize the way the hardware and software interplay happen for the networking devices. What this really means is that software defined is now disaggregation of hardware and software. So think of the control plane, the logical controller or the network operating system that we built, as an orchestrator that is able to manage multiple of these networking devices. And each of these networking devices, we would have the control agent that would run and facilitate configurations. And we would have the hardware, underlying hardware, which would dictate what hardware specific aspects that we would want to do. Now, taking this a bit forward, if we have to say that we can disaggregate this into rather a commodity hardware itself, that is, just as how we use our PCs, which are the commodity or off-the-shelf hardwares, we could use and build these routers on top of our regular laptops or personal computers and make use of hardware and software to build them. And in a way, we can have full control over what hardware we can use and what software layer that we would want to push. And this entire SDN framework would allow us to build these entire networking elements at a very low cost and in an effective manner. Nonetheless, it would not mean that we are moving completely away from the legacy protocols. The legacy protocols could still survive, and we could have the combination of hardware, proprietary hardwares or proprietary softwares to make them operate, but we would have the generalized interface for orchestrating on each of these devices. So, to give a good analogy of what it really means, if we think of the evolution in the personal computers, how this all began, the journey in the early 1960s, we had these mainframe devices, which were the mammoth devices that would almost fit half the room's size. But the main aspect there was they had the specialized hardware, and they would be operated with specialized operating systems, and only specialized applications would be run. And there was no scope for customization or enabling any user to try out different things. Whatever was shipped, and you had to take that for your needs. And this changed over time. And instead of having these vertically integrated or closed systems which were not open to innovation, And because of that, they were also deployed in very small scales. As the processor industry developed and we started with the era of microprocessors, which defined the open interfaces in terms of the instruction sets like x86 as an ISA, now which could be used and built multiple of the operating systems that would work on top of these processors like Windows, Linux, Mac OS, any of those. And these operating systems, in essence, provided the open interface for the applications to flourish. And that's what led to the growth, massive growth of personal computers. So these open interfaces are crucial for the evolution and innovations. And the same holds good now for the networking industry. Now with SDN, what we are trying to achieve is these open interfaces and which enables us to have rapid innovations as well. So to bring the analogy here, what we had were the dedicated switches and routers, where they were specialized hardware built by specific OEMs or vendors, and they had their own operating systems, and they would also have tailored applications that would be running on those dedicated hardwares. Now with SDN, what we have moved is from these dedicated hardwares to the merchant silicon switching chips or the commodity hardware. Like for example, this could as well be just our personal computers. And now we can run on top of these personal computers the network operating systems. And once we have these network OS that provides these open interfaces, we could build readily any of the applications at the top to utilize and run the required characteristics on these networking devices. And the open interface at the bottom would also mean that these commodity hardwares can now be programmed for the way that we would want the routers and switches to behave. And thus, this disaggregation of network industry has had a wide impact in the evolution of the 5G networks, the telecommunication networks, and the data center networks. And in fact, many of the campuses have started to deploy the SDN architecture for building the campus and enterprise networks. So this is a slide from Professor Raj Jain's presentation, but I would want to emphasize on how this disaggregation really moves us from a black box to the white box model. And what this really says is, earlier we had everything proprietary, and that was exactly the hardware and software which were completely as a black box. And now with the disaggregation that SDN brings to the table, we can have a complete white box model where the hardware is a commodity hardware and software is a commodity network operating systems that we would want to run. But it is not just confined to having complete white box approach. We could have still the hardware manufacturers from different OEMs like Arista, Cisco, whoever they be, Intel, all of those can still deliver the custom hardwares. But on top of these custom hardwares, now because of SDN, we are able to write the control agents for each of these onto the software and keep the software on top of which the applications are going to be written, that's the network operating system, the same. That way, we have disaggregated the hardware from the software and enable these open software implementations to run on these custom hardwares. And the other aspect, it could be an open hardware, but we want to experiment and run custom softwares that are developed by these OEMs. Even that is possible now, because if we can add and augment these softwares to utilize the open interfaces that were being built, then we would have a framework to test out those proprietary softwares also on these open hardware. And this is what was branded as the branded white box or the bright box model. So this SDN now with the disaggregation pattern is able to facilitate many mechanisms of how to run the network elements with proprietary or commodity hardware and software stacks. So to think of what we have seen is SDN bringing about a revolution in networking. And I would want to point to this article from the MIT Technology Review, which was published almost in February 2009 when Professor Nick McEwen made the statement about the SDN and what it really meant. It's just a one-page article here. I have also given the link for the interested readers to go and take a look. And this beautifully summarizes in terms of the challenges that then the network industry faced and what are the means and ways through which the software defined notion can be brought in and how this would even break the ossification or the impasse that we spoke of and open up for innovations in a much more ready manner. And to summarize, we have looked at the SDN in terms of how it all started with the RCP and 4D works, and we started to look into the emergence of SDN starting from the early 2008, where it meant to just centralize the control and logically decouple the control and data planes, and now to the stage where we are even thinking of disaggregation of the hardware and software stacks to build open networking elements. And this SDN, it all started with the Nisira as a company that started these open flow standards, which eventually got grown up and taken up by the IETF standards, and then the SDN working group started in the IETF, and then eventually it became a member of the Open Networking Foundation, which has many of the board members that we all know of: Google, Yahoo, Raison, Cisco, Juniper, all of them. And now this community in itself, the Open Networking Foundation community, which started in around 2011, has grown bounds and leaps. And in around 2022, there was a recent networking summit that happened in the very end of the last year. And the attendees were across from several countries, several of the interests were shown. And now we are seeing this SDN to have a greater emphasis and shape on the 5G and the NFV and the other tangential thing that we'll later going to discuss in the work. And this all has happened because of the way the visions were set for SDN.